Hello everybody. In this video, we're going to learn about the diagonalization of a 2 by 2 matrix. Well, what is diagonalization? The goal, to be more specific, the goal is we start where we're given a 2 by 2 matrix A. Let's say it has these entries, and we'd like to rewrite it in a so-called factored form. In other words, we'd like to write this matrix A as a product of matrices, a matrix P times a matrix D times a matrix P inverse. D is a diagonal matrix. It's where this process gets its name from. It's called a diagonal matrix because the non-zero numbers lie along the diagonal of the matrix from the top left to the bottom right, and all the other numbers are zero. And meanwhile, there will be another matrix called P with possibly 4 non-zero entries. It'll appear on the left side of D, and on the right side will be P inverse. So we want to find these special matrices P and D such that when you combine them in this way, they multiply out to give you the matrix A. Now that actually sounds like a lot of work, right? If you want to take a matrix and rewrite it as a product of 3 matrices, why on earth would you want to do that? Besides the fact that you love matrix algebra. Well, there is honestly a useful application of this process, which in turn will lead to other useful applications. In this video, the main reason we're interested in this is it will simplify calculating powers of a matrix. Now, we've talked about lots of matrix operations before. We've talked about adding matrices, scalar multiples, matrix multiplication, the matrix vector product, the inverse of a matrix. Now we get to add taking powers of a matrix to that list. So if we wanted to do something like, well, calculate the 10th power of a matrix, well, you do technically already know how to do that. You would just multiply the matrix by itself 10 times. Now, as you can imagine, that would take a fair amount of time. But as we'll see, being able to factor a matrix into this form makes this process a lot easier. This topic also ties in with things we've recently been discussing. In particular, the formulas for these 2 matrices, D and P, those actually involve the eigenvalues and eigenvectors of this original matrix A. So, to see an example of why this would be useful, as we just alluded to, let's say you start off with a matrix A. Let's just take the matrix 2, 3, 4, 1. Say I want to calculate a power of that matrix. Well, to calculate A squared, right, partition it into rows and then in columns. Calculate dot products, and you'll find that this matrix is A squared. To calculate A cubed, well, that's A squared times A. So you can take your previous result and then multiply it by A again and get this next matrix. As I asked you to imagine before, imagine how long it would take to calculate 8 to the 10th power. However, here's the advantage to writing the diagonalization of a matrix. Let's assume that we're able to take the matrix A and write it in this form as a matrix P times D times P inverse. Well, if you want to square the matrix A, and A squared is going to be P times D times P inverse times P times D times P inverse. Initially, you should be skeptical. Instead of doing product of 2 matrices, we have the product of 6 matrices. Even more fun, right? However, these 2 matrices that are next to each other, P inverse and P, those effectively cancel out. They multiply to give you the identity matrix, which does not change the matrix that it's getting multiplied by. So it's not really multiplying by multiplying 6 matrices altogether. It really amounts to multiplying 4 matrices. Again, Not a great trade-off, but it gets better the higher the power you want to calculate. For example, to calculate a cubed, that would be p times d times p inverse for the first a, times p times d times p inverse for the second a, times p times d times p inverse for the third a. This time we've got two pairs of matrices, p inverse times p. Both of these, that are also outlined in red, will cancel. We'll be left with p times d cubed times p inverse. This same pattern will hold. Hopefully these examples have convinced you that in general, matrix A to the power n can be written as p times d to the n times p inverse. And again, this looks like a lot of multiplications. Is this really a more efficient process? Well, it turns out a diagonal matrix, it's extremely easy to calculate the powers of a diagonal matrix because of all those zeros. Right? Imagine that your diagonal matrix is lambda 0, 0, I'll call that kappa, the Greek letter kappa, looks like a K. If I want to square this matrix, right, if I want to multiply this matrix times itself, then partition it into rows for the first factor, columns for the second factor, do your dot product calculations, and because of all those zeros, the answer is actually lambda squared 0, 0, kappa squared. Okay? D squared is equal to this. In other words, to square a diagonal matrix, you just have to square each of these entries. This is not true in general, but diagonal matrices are kind of great. In particular, calculating d to the nth power, exactly the same pattern, just like d squared has all these zeros, d to the nth takes advantage of all those zeros, and d to the nth power is really lambda to the n, 0, 0, kappa to the n. And so this matrix multiplication here, a to the nth power, well, d to the nth power, you can calculate very quickly, and then you really only have these two matrix multiplications. This matrix P times this matrix d to the n times the inverse of P. So you've effectively turned n matrix multiplications for any value of n, whether it's 10 or 100, you've turned that into two matrix multiplications, and that is a good deal. Now here is how this factorization, this diagonalization process, here's why it's related to eigenvalues and eigenvectors. So let's assume that your eigenvalues of the matrix A, let's call them lambda and kappa. And let's say that the corresponding eigenvectors, let's call them V and W. And so your matrix A has entries A, B, C, and D. And A times vector V is equal to lambda times vector V. And that's what it means for lambda and V to be an eigenvalue and an eigenvector. I can write A times V like so. That's calculating a matrix vector product. And lambda times V, well, that's scalar multiplication. And so I get this equation by expanding this out. And similarly, for A times the eigenvector W is equal to the eigenvalue kappa times the eigenvector W. And that simplifies and gets expanded to this equation right here. Now, let's say that P is the matrix whose columns are the eigenvectors. Right? So given your matrix A, calculate the eigenvectors and make those the columns of P. What happens when you multiply the original matrix times this eigenvector matrix, right, times P? Well, divide A into rows and P into columns, right, and each column is an eigenvector. Then when you carry out the multiplication, the product will look something like this. But then notice these terms. Right? They should look a little bit familiar. They're what we calculated up here. Right? AV1 plus BV2, that's equal to lambda times v1. So we could replace it by this. And the same with each of these other terms. In this matrix product, we can rewrite it in terms of the eigenvalues, which is admittedly a lot simpler. So that's A times P. Now, let's turn our attention to, just here I'm recording that information for future reference, the matrix D. The matrix D will be constructed by using the eigenvalues along the diagonal. And the order is important too. This first diagonal eigenvalue should correspond to the eigenvector used for the first column. The second eigenvalue, the one in the lower right, should correspond to the eigenvector forming the second column here. Now in this case, I'd like to calculate this matrix P, this eigenvector matrix, times this eigenvalue matrix. And if you calculate this out, this time we're doing P times D. So in this case, the eigenvectors, partitioning that along the rows, partition this along the columns, we multiply through, and here's what we get: lambda v1, kappa w1, lambda v2, kappa w2. This should look familiar. This is what we just calculated on the previous page. These two are equal, so that means A times P is equal to P times D. Now if we want to isolate A on one side by itself, we could multiply both sides of this equation by P inverse on the right. The P and the P inverse cancel on the left, leaving you just A. And on the right, you have P times D times P inverse. And so that's how you get the diagonalization of a matrix. Given a matrix A, calculate the eigenvalues. That gives you the diagonal matrix D. And calculate the eigenvectors. And those are the columns of the matrix P. And you'll also have to calculate the inverse of this matrix P. But since we're only working with 2 by 2 matrices, there's a nice formula for that, and it's pretty straightforward. So let's do an example. Let's find the diagonalization of a matrix A. We'll use it to not only calculate the cube of a matrix, calculate A cubed, but we can also derive a formula for the nth power of a matrix. So to start off, let's say that A is the matrix 1, -2, 1, 4. To calculate eigenvalues and eigenvectors, we need to calculate the characteristic polynomial of this matrix. And that's the determinant of the matrix A minus lambda times the identity matrix. So we subtract lambda from these two entries. Then we have to calculate the determinant. Remember, that's the top left times the bottom right minus the bottom left times the top right. And so calculate that. Expand this product here. And we'll multiply that out. We get the two negatives here cancel and give us a positive. And then we have a nice quadratic equation. We're going to set that equal to 0. And fortunately, that happens to factor again. All these examples are chosen so that they factor nicely. And when that factors out, that tells us the eigenvalues will be 2 and 3. Right? And then that information tells us that this is our diagonal matrix. It has the eigenvalue 2 followed by the eigenvalue 3. So we're about halfway there. Now that we know the eigenvalues, I'll call the first one lambda and the second one kappa. Now that we know the eigenvalues, we have to find the eigenvectors. And we've done this before. And we're calculating A times the vector v is equal to lambda times the vector v, and we want to solve for v. And the way we've done that before, we'll insert an identity matrix on the right-hand side between lambda and v. Then move that term to the left. The reason for inserting the identity matrix is that allows us to factor out the vector v. And then, well, we have to solve for v. So for this first case, lambda equals 2. So we're subtracting 2 from these entries. Right? This matrix is A minus lambda times I times the eigenvector v1, v2 is equal to the 0 vector, 0, 0. We can rewrite this as a system. And as you may remember, whenever we're finding eigenvectors, right, the system of equations should look redundant. There should be a free variable in there. And because there's actually infinitely many eigenvectors for each eigenvalue. So in this case, you notice that the second equation is actually the negative of the first equation. That's a sign we're on the right track. To make the numbers work out nicely, maybe for v1 we'll pick -2, and v2 we'll pick 1. So that'll be the eigenvector that we use. Again, there are other correct answers that would lead you to other diagonalizations, and they would work just as well for this problem. We've got our first eigenvector for the eigenvalue lambda equals 2. Next, let's find the eigenvector for the eigenvalue kappa equals 3. So we're setting up the same equation, do the same manipulations, subtract that eigenvalue from these diagonal entries. We'll convert this into a system of equations. Again, there's some redundancy in this equation, right? The first equation is -2 times the second equation. So there's a free variable there. We'll pick w1 equals 1, that's pretty simple, which forces us to pick w2 equals -1 so that the equations have a solution. And so that's our second eigenvector. And then these are going to be the columns of our matrix P. And so to summarize what we've done, the matrix A, 1, -2, 1, 4, has eigenvalue 2 with eigenvector -2, 1. It also has the eigenvalue 3, and we picked the eigenvector 1, -1. So the diagonal matrix D is 2, 0, 0, 3. The eigenvector matrix P, so the first column is -2, 1, and the second column is 1, -1. And then we need to calculate the inverse of that matrix. Right? So first, it's 1 divided by the determinant of this matrix. The determinant, let's see, that's -2 times -1 minus 1 times 1. Hey, that's 1. So that's a nice factor to multiply by. And then, as always, in the inverse formula, you have to switch these two elements, so -1 and -2. On the off diagonal, we have to negate those values. And there is our inverse matrix. And along this way, there's so many times you can check your work. I love math problems where you can check your work and be confident and move on. At any point, you could, for instance, calculate A times V, check that's equal to lambda times V. You calculate A times W, check that that's equal to kappa times W. To check your inverse, you could multiply P times P inverse, make sure you get the identity. To make sure everything's okay, you could have checked that A does equal P times D times P inverse, right? Multiply these three matrices together, make sure you recover the original matrix. We can assume we're pretty confident in our answer, I think. So how would you use this to calculate A cubed, right? So in this case, A cubed would be P times D cubed times P inverse. D cubed, right, to calculate the cube of a diagonal matrix, I'm going to cube these two entries, raise them both to the third power. 2 cubed is 8, while 3 cubed is 27. And now we just have to multiply P times D cubed, right, doing my row and column partition, calculate those dot products, and you'll get this. And then after multiplying those two matrices together, I have to multiply by the third. So multiply that by P inverse. And this is what you'll get for A cubed. And it is a similar amount of work to say calculate A to the fourth or A to the fifth or A to any power. You just have slightly larger numbers here in the middle. It's a good time saver. Now here's how you can use it to actually create a formula for any power of a matrix. In this case, Instead of figuring out what the numbers are for d to a particular power, d to the nth power is, well, each eigenvalue raised to the nth power. We just leave the variable n in here. And now to calculate a to the nth power, once again, we'll multiply p times d to the nth power. In this case, this is what you'll get. Right, this actually looks really nice and simple because we're multiplying by a lot of ones, and this -2, this 2 happens to be the same as this eigenvalue. That won't always happen. We'll see in another example. But in this case, since we have 2 to the n times another 2, we can just write the exponent as n plus 1. And then we multiply this matrix times P inverse, and we get some more terms here. But that's actually pretty simple. And to check this, because as always, it's good to be able to check your work, you could try plugging in n equals 1, in which case you should get the original matrix A. You could plug in n equals 3, and you should get a cubed, which we calculated on the previous page. And then if you really want to calculate a to the 10th power, you can do that. Just plug in the 10s here in each position. All right, and that's how you use diagonalization to derive a formula for the power of a matrix. We should do one more example. So let's try this one. Let's say we want to diagonalize the matrix A, which is -4, 1, 7, and 2. As always, to diagonalize, we'll need to calculate eigenvalues followed by eigenvectors. For eigenvalues, we're calculating the determinant of this matrix, A minus lambda times the identity. So we've subtracted lambda from those diagonal entries. Then to calculate the determinant, it's top left times bottom right minus bottom left times top right. Go ahead and expand this out, collect like terms. As usual, this is going to factor, and we get that our two eigenvalues are -5 and 3. For each one of these, we go through the same process to calculate the eigenvectors corresponding to each eigenvalue. So first, maybe we'll do lambda equals 3. Set up this equation as usual. In this case, here's our original matrix A, subtract that particular eigenvalue, convert it to a system. Just a quick check tells us this is a free variable in this system because the second equation is a multiple of the first. Pick some nice easy numbers. Say V1 is equal to 1, which forces V2 equal to 7, so this stays equal to 0. So there's your eigenvector. Same process for kappa equals -5. In this case, you're subtracting -5 from these entries, so that turns into a +5. Right? Multiply that by that vector, change that back into a system of equations, and this is particularly nice, right? Because W1 plus W2 equals 0, well, I'll just pick 1 and -1 for those values, and that's the eigenvector. Now that you have those, we can immediately write down the diagonalization, right? The only thing we have to be kind of careful about is keeping things in the right order. Right? Remember, if lambda goes here, lambda's eigenvector is the first column. So here, the diagonal matrix is 3, 0, 0, -5, because those were your eigenvalues. And the eigenvector matrix, P, the first column is 1, 7, and the second column is 1, -1. From this, we can calculate P inverse using the formula for the inverse. This matrix has a determinant of -8, so everything will get multiplied by a factor of -1/8, giving us this matrix as P inverse. So 1/8, 1/8, 7/8, and -1/8. To calculate a formula for a to the n, same process that we used before. P times d to the n. Right? Be very careful about your parentheses when you have a negative value. It's the negative value which is getting raised to the nth power. Right? And you can go ahead and multiply that through to get the final form for the power a to the n. Right, so that's how diagonalization works. And as we'll see in the next video, diagonalization helps us actually answer some really interesting real-world questions. But as I always say, you learn math by doing math. So here's an exercise. Now, let's do this problem a little bit further. Let's calculate a cubed in two different ways for this particular example. Right, first calculate a cubed the way you would have done before this video. Actually multiply this matrix times itself 3 times. Right, this matrix times this matrix times this matrix. And then calculate it using the diagonalization formula. Right, in this case, we're going to raise the eigenvalues to the third power, and then just multiply these through. And, assuming everything works out here, hopefully there's no math mistakes, you should get the same answer in both of these expressions, which gives you a way to check your work, which is very convenient. But go ahead and give that a try. And that's all there is to say about the diagonalization of a 2 by 2 matrix. Thanks for watching.